Good afternoon, everybody. I'm Sashank Tirumala and I'm here to present our paper Learning Stable Maneuvers in Quadruped Robots from Expert Demonstrations. This work was done in the Robert Boss Center for Cyber Physical Systems at the Indian Institute of Science, Bangalore. In this work, we use our in-house developed quadruped robot Stock 2, which is the successor of our previous quadruped robot Stock 1. Stock 2 is a highly dynamic and versatile quadruped robot that is capable of omnidirectional motion. It uses about 3 servo motors per leg and a TIVA M series in order to control the servo motors. The total runtime of our quadruped robot is about 20 minutes. So the motivation for our research. Recently, we've been seeing a number of quadruped robots enter the commercial market, like Spot from Boston Dynamics, like Cargo from Unitary Robotics. Similarly, we've been seeing a number of open source quadruped robots, like the Stanford Doggo, the NYU Solo, and our own stock quadruped robot. However, similar to driving a car, it requires expertise to handle a quadruped robot. Can we create a user-friendly controller for such a quadruped robot? So let us first find out what happens when a novice user handles a quadruped robot. In this case, the novice user, he is trying to change directions from left to right. As you can see, the robot loses balance and it starts heavily damaging the motors. Even in this case, when you are standing still to turn, a large amount of slipping occurs. However, an expert user is capable of performing such maneuvers in a smooth and stable manner. Let us take one such example. On the left side, we have the novice user's joystick commands. On the right side, we have the expert user's joystick commands. The green stands for the radius of curvature or direction, while red stands for the speed. As you can see, the novice user abruptly changes the direction while not affecting the speed at all. On the other hand, the expert user gradually changes the direction. At the same time, he reduces the speed while the direction is changing and then increases the speed back up to normal once the direction has changed. If you were driving a car, this would be very similar to how you slow down before turning. However, in some ways, it is much harder to handle a quadruped robot than handling a car. That is because often you have no line of sight to your quadruped robot, thus you do not know if it is slipping or not. Then you have no sense for velocity. Often you will not slow down enough since you do not understand how fast the quadruped robot is moving. Finally, the quadruped robots tend to be very brittle. If you put too much load on the motor's gears break. Replacing the gears of a motor is a very painful and lengthy process. So in this slide here, I show 3 examples of novice user data and corresponding expert user data. A naive approach would manually code a filter for each of these transformations and then would use if-else conditions to change between the filters. However, such an approach would not scale. We have at least 10 such transitions, and in total we have 200 generalized transitions that we perform. A better approach would be to take a neural network that converts the novice user data into the expert user data. That is what we do. We use a neural network to convert the novice user to the expert user data. However, standard neural network architectures are not good enough. So we add some structure to our architecture. The neural network can be written as a weighted average of simple filters of the joystick input. As an example, these pre-trained filter networks, their weights do not change. All they do is they perform simple filters of our joystick input. Simple filters include moving average filters and exponential filters. On the other hand, our trainable network consisting of 10 convolutional and 2 supervised learning layers, they output the weights that are used to perform the weighted average of the simple filters. Due to this, our neural network gains good properties of filters like time and scale invariance. Let us see the output from our neural network. This is when we are moving left to right. There is no slipping at all and our robot stably moves from left to right, as you can see. Similarly, when moving still to sudden turn, no slip at all. Now let us compare the results to a standard filter. A standard 2D convolutional filter cannot copy the expert data. However, our neural network performs an exact copy of the expert data as we see in this third row over here. Now let us compare our neural network to architecture to other common network architectures like fully connected and convolutional neural networks. Fully connected is green in color, convolutional is blue in color. Our proposed architecture is red in color. A, B, C are three different data sets, and in this bar graph we are graphing the validation loss. Clearly, our proposed network architecture has a much lower loss than other common neural network architectures. For dataset B and C, our loss is almost negligible at the range of 10 power minus 3. Finally, let us talk a bit about the controller for our quadruped robot. It expands upon the work in trajectory-based deep policy search that we submitted to the previous RoMan conference. In that work, we parameterized our trajectory with a rational Bezier curve and filed optimal parameters using augmented random search. In order to turn, our robot expands upon the work done on the Oncilla robot by Degrave et al. We use similar formulations to enable our robot to turn. These here are the equations for our robot to turn. Phi is the angle that the robot makes with its body as shown over here. SL is the step length. J is the optimization criteria with its energy plus the penalties. Let us see the entire system in action. Transitions plus the standard rotations. This here is the joystick control of the robot. This is the robot moving in a 70 centimeter radius. $50. And it moves in a spiral till it moves on spot. Finally, I would like to thank all my collaborators Sagar, Aditya, Karthik and Shishir, and I'm free to take any questions.